three sentences about pressure. One of them is pressure increases with depth. I'll leave that go for now. The second one was pressure always acts perpendicularly to a surface. So this is a gas inside some sort of container. Every time the gas particle hits off the surface, it rebounds like a snooker ball off a cushion, and it experiences a force perpendicular to the surface because the particles are hitting perpendicular to the surface. So pressure acts perpendicular to the surfaces. The second one is pressure is caused by these particles exerting force on the container. So it's a bit like the average force per second per meter squared is the pressure that will be displayed on this gauge here. So there are a couple of ways to increase the pressure. One of them, like in the formula P is equal to rho GH, is to increase the density. So if I have more particles, we have a denser gas in here. Denser gas means there are more particles hitting off the surface per second, so we'll see the pressure goes up. So let's increase that a bit more, and you can see it there immediately. Greater density in here, greater pressure because there's more particles colliding off the container surface per second. Now that's not the only relationship between pressure and another quantity. If I was to heat up the gas molecules, they travel faster. Gas molecules that travel faster hit more frequently off the surface of the container, and as a result, as we can see, the pressure increases. Conversely, if I cool down the particles, they slow down. If they slow down, they hit off the surface less frequently, and if they hit off it less frequently, it's the same as having the pressure decrease. And there's one other one. So if I decrease the volume, in decreasing the volume, I'm increasing the density in here. These particles hit off the container more frequently, and as a result, the pressure goes up. So if I do it once more, it was at 49, now it's gone to 62. Okay, time for some real world stuff. There's some interesting videos for you. So when we're dealing with questions, we always deal with pressure difference. And I'm going to start by talking about the pressure difference inside and outside fish. So on the left there, we've got a fish that exists 3,000 feet below the sea level. And below the sea level at that depth, there's a certain pressure due to the liquid around the fish pushing in, but the fish's body is created to deal with this, so there is a pressure pushing outwards that is equal and opposite. So the pressure balance between in and out is within a certain acceptable limit for the fish. Now, if you were to pull that fish rapidly to the surface of the ocean, you'd get what we see on the right. So what's happening here is there's a pressure pushing out, there's a pressure pushing in, that in its natural habitat seems to be comparable. But when you pull that fish up to the surface, what ends up happening is the pressure pushing out is much greater than the pressure pushing in, so the fish has some sort of unusual reaction to it. Now, I have a friend and she studied fish like this, and she told me what happens is the pressure pushing out is larger than the pressure pushing in, and usually what happens is the stomach comes out of the mouth like that and the eyes pop. Now this would be the same thing that would happen to an astronaut if they were ejected into space. Okay, that is before they freeze to death. It also happens when people climb mountains. So when you climb a mountain, you feel lightheaded. Your stomach doesn't come out your mouth and your eyes don't pop, but it's the same idea with the pressure. You feel lightheaded, and also the density of air is vastly decreased, so you have difficulty breathing. And we'll see there in a minute that, or we'll see in a different video even, that your lungs are affected in that regard as well. Okay, moving on. So like I said, we're thinking about pressure difference. So now we're going to submerge an object, and we're going to look at the pressure acting above the object and the pressure looking below the object. So if we look at the top of the object there first, I'm assuming that all of that is submerged in the liquid. The depth of the top of the object below the liquid is much less than the depth of the bottom of the object below the liquid. That means the pressure acting on the bottom of that substance is greater than the pressure acting on the top of the substance. We know that pressure is equal to force over area, so force is equal to pressure by area. So therefore, what's happening is there's a greater force pushing up on the bottom surface than there is pushing down on the top surface. As a result, this block experiences a net upward force. So pressure is greater below than the object and above. So this leads to a net upwards pressure, which in turn leads to a net upwards force. We call the force an upthrust or a buoyancy force. And what it ends up doing is it makes objects appear lighter in fluids. So when you go to the swimming pool and you jump in, you feel lighter yourself. And the reason for that is there's a height difference between the top of you and the bottom of you, and on your feet there's a greater force pushing up than there is on your head pushing down or on your shoulders pushing down. So there's an upthrust acting on you. Okay, it'll be time for you guys to watch some videos now. I'm going to keep going. Okay, does the object sink or float? So when we look at an object that's submerged in a fluid, we'll have two forces acting on it. If it has a mass, it's got a weight, so there's a weight acting vertically down. And if it's in the fluid, it has this upthrust or buoyancy force. If the buoyancy force is greater than the weight, it means the force up is greater than the force down. That means the object will go to float. It'll rise up and float to the top. Now, if we go to the third one, if the buoyancy force is less than the weight, so the weight is acting down, is trying to pull the object down, and if the upthrust or the buoyancy is less than that, it means that the object will sink, but it will feel like it's not as heavy as if it was in air. And then the third case is a special case. If the buoyancy is equal to the weight, the object will stay where it is. Because according to Newton's first law, if an object doesn't experience any net force, it won't accelerate. Okay, we have an image to show the three of those. The middle one there, look, if the weight is equal to the buoyancy, you can put the object anywhere in the liquid and it will just sit there and stay there. We rarely see this because to have that happen exactly is very, very difficult. The one on the right is when the weight is greater than the buoyancy, so it sinks to the bottom. And the one on the left is when the buoyancy was greater than the weight, so it rose up. And eventually what will happen is the object will reach the surface. It'll sit on the surface with part of the object submerged and part of the object above the surface. And when it does that, then it's at rest. And in that case, the buoyancy that it experiences is equal to the weight. The left-hand diagram, though, the buoyancy there is going to be less than if it was fully submerged. So that's something to take note of. Okay, so if the object floats, there's no net force on it. And look at the diagram, it says the weight of the object equals the upthrust acting on the object. There's the second. In that case, again, we have a buoyancy force or an upthrust equals the weight of the object if it's floating. Okay, end of the second video.